So we're going to start our second morning session now, continuing this theme of open data and open science with the critical component of how do we contribute, which I'm always learning from because to me, sharing my code is still scary. So I would like to invite Max Grover to come up and share how we can contribute to open science in our fields. So take it away, Max.
Let's see. Alrighty, yeah, so I've changed the title a couple times as the week's gone on. So on the path to contributing to open science. My name is Max Grover. I'm a software developer at Argonne National Lab and work a lot with a few different projects. So I swear, this is not going to be a GitHub or Python tutorial. I promise. We're not going to actually dig into GitHub and stuff like that. This is going to be more so a general how to contribute, a little bit about my story into this realm, and some best practices and that sort of thing. So a little bit about myself. Background in atmospheric science. I interned at Unidata in 2019, worked with Ryan May on all things MetPy. Went on to get my master's at the University of Illinois, looking at severe storms, worked at NCAR for a year, and then ended up working on open source software and working on different packages at Argonne National Lab. So Unidata was really my first experience in the software engineering realm. I had used packages, I had used MetPy, I had used all these core tools before. But this was really the first time that I got started actually working on some of these different packages and contributing and becoming more familiar with this open science space. So an overview of open science. I really like this figure from the NASA TOPS team. And this sort of breaks down sort of all the components. So you could see open science there in the middle. And sort of the three main themes, which are accessibility, reproducibility, and inclusiveness. And sort of the key components I'm gonna talk a little bit about today is the open data and fair software, the open collaborative analysis tools, the open tools and frameworks, as well as just new pathways to science. And these are all very critical pieces of sort of this open science story. So kind of how I got started. So learning the basics of open science. Spoiler alert, this is going to be very Python oriented. I love Python. And so, yeah, a lot of my first experience with open science and getting into that space is working with open data hosted on different Unidata thread servers. So a lot of this was meteorology classes where we were looking at different weather maps and that sort of thing. Pointing to some URL that was pointing to one of the Unidata thread servers or one of the NOAA ones or that sort of thing. And then using MetPy and the Python programming language to actually work with some of these different data sets. So this sort of was the foundational introduction to open science. And then from there, like I said, sort of got started at Unidata. And similar to like Scott was saying, you often want to start with some sort of project where, does anyone know what this block of text is? Yes? METAR. Yes, the joys of METARs, which is a way of encoding surface observations. So that was my summer project. That was all focused on sort of figuring out how the heck to parse these in a generic way. It had been a feature that people had been asking for a while within the MetPy Python package. And so that summer was spent taking that block of text, figuring out a generic way of parsing that, and then creating some of those different maps. So that was a neat way of sort of finding out how to even start playing around with some of these different Python packages, the idea of writing tests and that sort of thing, and then finally contributing to it. And it definitely took a bit to figure out that initial process. So going from that user contributor process can be really challenging. There's a lot of things that get in the way. So some hurdles along the way. The first question is like, can I even do this? So many people use this tool. It's terrifying, especially when it's used in classes and that sort of thing. And it's such a core part of the community. That imposter syndrome definitely comes up about is this, am I capable of doing this and stuff like that? And that fear can sort of get in the way of committing your code and contributing to this space. How do I even add code to the project? Like a lot of people just import different packages and that sort of thing, and just how do you even go about that process? So that Git /GitHub workflow learning curve can be pretty steep, especially as somebody who's in more of a domain space like atmospheric science and that sort of student space, and even computer science classes and stuff like that won't necessarily dig super deep into the Git workflow. So there is that big learning curve in terms of initially figuring out how to contribute code. And then also the formatting, which you don't necessarily think about, like when you're using the package and that sort of thing, you can kind of format things however you want. But then actually committing it to a shared repository and some of these different standards and that sort of thing, getting all different sorts of what we call linting errors, which is where am I supposed to use a single quotation, double quotation? It can be really confusing. It can be really discouraging when you have this new thing you want to be able to contribute. You want to add it to the space, and then you get all these errors saying that your code's awful. Like it doesn't pass some of these different checks. So that can be some big hurdles and some issues that sort of get in the way. So after quite a bit of feedback and sort of going back and forth on this process, the first pull request got merged. I added some altimeter calculations within MetPy, and just sort of getting this first step was really exciting, and it was frustrating at times, but to finally get that in was really exciting. And so there's all these different challenges that get in the way, and here's some general advice for sort of getting past some of these. So kind of along that imposter syndrome, everybody starts somewhere. And there are these different safety checks and stuff like that in place. So for example, with some of the MetPy side during that summer, there's the idea of like writing tests and that sort of thing, and sort of creating this initial prototype that after it gets reviewed and that sort of thing, then it finally goes into sort of the main code base. In terms of adding code to the project, something that I didn't necessarily realize at the time, but something that's sort of come over time, is that it's not just code. Sort of like Scott was saying earlier, there's so many other ways to contribute, whether it's different support, just flagging an issue with a package and that sort of thing. Definitely ask for help and that sort of thing along the way. And then kind of along that last line, the linting and some of those issues, there's a lot of automated tools now to be able to help with that. And also don't be afraid to ask the different maintainers and stuff like that for help. So that was a little bit about the initial contribution and sort of getting started in this space. And now I'm going to dig into a little bit about open data, which we've already heard a lot about so far. So the main programs that I work with are the Atmospheric Radiation Measurement User Facility, which is sponsored by the Department of Energy. That's one of the facilities that's located near Crested Butte, Colorado right now. Then I also work quite a bit with the Crocus Project, Community Research on Urban and Climate Science, which is a project all focused on urban climate around Chicago. And so both these projects are producing different data sets, and beyond just data, a bunch of other toolkits and that sort of thing. But I just want to kind of provide some perspective on open data in the context of these projects. So when it comes to open data, it's critical to have some of these different data portals. So this is an example of ours for the atmospheric radiation measurement user facility, where it enables that sort of fair access. So that's an example of one of our radars there on the left. That's just one of the different measurements you can get from the portal. So these data portals are super useful when it comes to finding data, finding like what area you're looking at, along with just making it user-friendly for people to find the data that people are creating. But beyond those data portals, there's a lot of data there. For the ARM program, we have roughly 5 petabytes of data with so many different data streams, everything from radars to different ground-based measurements, time series data, that sort of thing. And so it's tough to be able to work with this, especially since that's not going to fit on your laptop. So something that's becoming increasingly important is the idea of coupling it with some of these different Jupyter Hub interfaces and actually providing this data proximate compute, where you can see here that combining like the ARM data with sort of this Jupyter interface, get right to your analysis and that sort of thing. And so it's increasingly becoming important that we have these different platforms that are located right next to the data. Along with these platforms, we have different toolkits that we support. So the main package that I work on is the Python ARM Radar Toolkit. So this is building on a bit of what Scott was talking about earlier, initially created by Scott and Jonathan, and has since had roughly 50 contributors to the package, a big community that has come around this package. We have about 1,000 monthly users according to the documentation, as well as several citations. And this package is really all built around working with weather radar data. So it was originally built to work with ARM's research radars. It was built specifically for the ARM program. But over the years, it's continued to expand and to support other types of radars, such as the NextRad radar network, along with about 13 other radars. The whole idea of the package is to get it into this common radar object, which is common within Python. We're getting a common object, and then we can go through and apply different corrections, retrievals, gridding, graphing, and all that sort of thing. So at this point, I just wanted to demo this, since we were talking about data and some of these different toolkits. So let me go ahead and escape. So it's on the Jupyter Hub. So if you go under today's workshop, Thursday, if you go to Grover Open Science, you'll see this. So this is the Python ARM Radar Toolkit. So you'll see within this notebook, this is something that we use for different trainings and workshops and stuff like that as well. But this kind of gives an overview of the package. So we see general overview of the Python ARM Radar Toolkit, an overview of this radar object, and then creating a plot of our radar data. So you'll also see there's some prerequisites here. So I'm not going to be able to dig into everything, but you could see if you go ahead and click on some of these, for example, mapping, intro to Cartopy, you can see some of that content. We also have matplotlib basics, which is a common tool when you're working with data visualization in Python, and then you can also see NumPy. So we're going to go ahead and run our imports here. So we imported PyArt along with some other tools here. I'm not going to actually go through and read some of this. I encourage you to read through it at your own time. And the data set we're working with today, so as I mentioned, we have roughly 5 petabytes of data through the ARM program. The specific data set we're going to go through here is from the SAIL field campaign. This is the Surface Atmosphere Integrated Field Lab. This is a view of the radar. It's a beautiful location out near Crested Butte. And so, yeah, let's go ahead and work with this. So the first stop for people when they're working with this radar package is the io.read module. So this is how you actually read in the data. So we could see some information here about a general idea of what this is doing, what it takes in. And so we're going to load in one of the sample files here. It gets it into that radar object. You can go ahead and look at some of those different fields. So we have corrected velocity, which is towards and away from the radar. We have reflectivity, along with a bunch of other fields. So from here, we can go ahead and take a look at one of these individual fields. You can see it's an array with lots of different values. You can check the shape and that sort of thing. But now down here, we're going to go ahead and plot some of our radar data. So usually the user reads it in to that radar object and then usually plots it. So we set up our display here. This is what we call a radar map display. So it's going to add the latitude and longitude and give us a little bit of frame of reference. This specific radar data was from a snowfall event from March of last year. So when we go ahead and run this, you'll see that as you saw in that animation, we're in the mountains, and so the radar beam is actually running into some of the terrain. So that's why we're looking at the lowest elevation here, and we actually can't really see much because the radar beam is hitting those nice mountains. So we can go ahead and change some parameters here. So we can go ahead and move up in terms of kind of going higher elevations. We can specify some of our plotting, like our minimum, maximum for our color bar. We can change the projection and that sort of thing, add in some latitude and longitude lines to make this a little bit prettier. And then we can also save our figure. So if you run that cell, it's looking up a little bit higher. So that's looking at 6 degrees above the surface, and we can actually see some of the snow bands there off to the east of the site. So from there, we can go ahead and do some additional customization, that sort of thing. We can change our color bar if people want to use a different color bar. Another common type of radar data is range height indicator. So this is actually like a vertical cross section through the atmosphere. So we go ahead and do that. You can actually see sort of some more vertical structure from the storm, where you can see those nice snow bands close to the radar. So that was kind of a quick overview of the Python ARM Radar Toolkit. It's really important with a lot of these different data sets that we have with the atmospheric radiation measurement user facility that we support packages like this, because we don't want people just to download the data and have to figure that out themselves. Having these concrete examples and supporting toolkits for people to be able to analyze this, and also for people to contribute this back. So for example, if people have cool plots and stuff like that of some of the neat data they're working with from some of these different campaigns, this sort of provides them a way to contribute it back. I'm going to go ahead and jump back to here, and we'll keep moving along. So that was sort of one example of working with radar data from the Sail Field campaign. This is an example of one of the data products that we worked on. So this is actually estimating snowfall liquid equivalent from some of this radar data. And so we actually developed this cookbook that actually walks through this whole process, where it is a data product that we provide to the community, where we provide the netcdf files and they can go ahead and work with it. But we also provided the fundamental code where if they wanted to go back through and apply their own relationships and their own derivations of some of these different data sets, they can do that themselves, which is really nice. And it's led to additional features being added within the core Python toolkit. So some lessons learned, kind of publishing some of these new data sets and developing some of these different toolkits. Use some of these metadata-friendly formats, such as netcdf. So when we submitted this, if we go back here, so when we submitted this data set, there's actually a whole review process in terms of making sure that the proper attributes, making sure we have units and that sort of thing. And when you're publishing some of these different data sets, it's critical to include a lot of those data formats. And fortunately, we have a format like NetCDF, which is the standard across the whole program to be able to describe your data this way. Ensure you assign the proper units. That's something always good to make sure you do when you're contributing any sort of open data, because sometimes you can mess up and lead to some very bad results. Add tests to your processing chain. So sort of in the similar sense of software, it's good to add tests to make sure that things are doing what you think it should be doing. So this was brought up in the previous talk, but actually versioning your data is really important, because sometimes products need updates. So if we go back to this one, so for example, if we accidentally added an extra 0, or if we had like some sort of extra relationship we wanted to add, it's critical to add those actually versioning your data, so that way people know that they're getting the latest version, and that way they're not messing up their analysis using some sort of error data set. Share examples, accessing and using your data set. So like we did with that previous example using some of the sale data, it's important to share your examples and show people how to work with the data, so that way they can jump right in, get started, and really dig into the analysis without having to recreate the wheel. And then DOIs are always super important, and offer a way of sort of giving credit. So similar to Neon, the ARM program, especially a lot of the field operators and everyone that's been involved with creating that data set, is credited to some of these different DOIs. And so during that process, it's critical to make sure that people get credit and that people are citing those different digital object identifiers. So the last portion I want to talk about here is the need for workforce development and some of these different training and onboarding ways of getting into open science. So some gaps in some of this open science education. There's so many tools to choose from. It's hard to choose one to pick and where to get started, because you might be afraid of, if I start with this one, is there going to be like a new one in like a few months that it's already going to be outdated? There's not always a one-to-one example of what people want to work with. So for example, let's say you're working with looking at like temperature over like Wisconsin, and you're not sure if there's like a similar example, like, but you're interested in like North Carolina or something like that. Like there's not always going to be like a copy and paste and just jump right in and everything works magically and you're done with your analysis. And it can be tough to balance packages versus workflows. So a lot of the individual packages will have their documentation, but oftentimes you want to use a collection of packages. Like let's say you're using one to access the data, you're using another one to actually analyze it, and then you're using another one to sort of save things out. You sort of need those general workflows. And that's where I really want to make a plug for Project Pythia. It's come up a couple times this week. It's a National Science Foundation funded project that really focuses on educational materials and sort of being the one-stop shop for getting started with Python and the geosciences. But I'd argue it's more so just open science in the geoscience in the geosciences. And people mentioned Pangeo earlier, and this is sort of the educational wing of Pangeo, just trying to get people onboarded to all these amazing tools to work with open science. And there's sort of a few main places on the Project Pythia place to get started. So there's looking here, there's the foundations content, which is really focused on those core foundations such as Python, such as Xarray, which we've heard a couple times with pandas. And then there's cookbooks, as well as resources, which is sort of the broader like videos and external packages and that sort of thing. So I want to focus specifically on the cookbook part of the Pythia space. So this is something I've been heavily involved with, and something that I think in this open science space, this is where I think there's a lot of room for growth and a lot of room for opportunity and sort of some low-hanging fruit. So when ARM, when we were sort of talking about cookbooks, we didn't necessarily want to invent it, like avoiding like not invented here syndrome, where it's like we don't necessarily need to have our own separate project and that sort of thing. And we've worked with Project Pythia, where I'm not necessarily funded directly under the grant, but we've worked with them to contribute the first cookbook, which is the Radar Cookbook. So this is sort of an overview of the cookbook structure. So we know that people want to work with radar data. We know that they're going to need that sort of overview of the Python ARM Radar Toolkit. And then we have these different workflows. So say somebody wanted to do corrections, or another person wanted to do some cleaning and stuff like that. So we sort of identified these core spaces where there's some crossover, and we could sort of have some shared resources. And then the other really nice thing is we were able to plug in some of the existing material, like I was mentioning, the foundations material, which really focuses on those core foundations such as NumPy, which is for working with arrays, Matplotlib, which is for data visualization, and Cartopy, which is for mapping. Where we didn't have to write that ourselves. Like within the ARM program and within PyArt, we didn't have to create that material ourselves. We could leverage the existing material and contribute back to this already existing awesome project. So our first cookbook was the Radar Cookbook, and there's since been a bunch of other cookbooks. This is sort of the main one I'm involved with, and there's a whole community built around these different cookbooks. But this is an example. So this is one. It's all focused on radar data. We mentioned PyArt quite a bit here, but it walks through the basics. We have the corrections as well as gridding. So those are three common parts that people want to work with. But then we also have these concrete workflows, like looking at NextRad, that's the weather radar network across the U.S., data from Moore, Oklahoma, which was a big tornado. Plotting data from a field campaign. So that's from the Tracer field campaign, which is in the Sierras de Cordova region of South America. And then, Cacti, that's that last one. Then Tracer was down in Houston, Texas. And so through working with Project Pythia, we put together this cookbook where now we sort of point anyone who's interested in getting started with radar, working with weather radar data, and really digging into that open science space, point them here. So they can get started and really jump right into their different workflows. So cookbooks are one part. Another critical part is tutorials and workshops. So this image on the left is actually from the summer after I was at Unidata. We did a Python workshop at the American Meteorological Society annual meeting, where for years they'd have like a dedicated short course that morning for sort of the broader community, not really including students. And so one of my focuses that summer was sort of asking if Unidata and sort of the program and would be willing to help with some of this. And I worked with the team to help put on this workshop, which supported by Unidata and all these awesome people. And we educated 140 students that day on how to get started with Python and really get started in this open science space, which is awesome to be able to work with that many students. We had a lot of really fun modules and stuff like that. And this is a critical part of continuing to grow the community, be able to support this hands-on support. Like I was saying, the imposter syndrome, like actually being able to meet some of the different developers and stuff like that and actually put a face to some of these different packages is so important. And so the other tutorial that we put on, so this was when I was involved with ARM, we did an open science in the Rockies where we focused on that SAIL field campaign and brought in, that's one of the principal investigators of the project up there on the screen. But we actually worked with providing the platform and some of the materials and stuff like that in the space to be able to educate people on how to work with some of these different data sets. And one of the coolest things about that workshop was this was on Sunday of the week of AMS, and we actually saw somebody on Wednesday during their talk using a figure that they had generated from the materials from the workshop in their presentation on some of the science of the field campaign, which is awesome. Like it's just neat seeing the cool things that people do with this, and he's continued to be involved with the project. So So these sorts of tutorials, workshops, outreach are critical to the mission, and that's something, again, grateful that Unidata supports a lot of this as well. One other component of education outreach, like Scott was saying earlier, communities of practice, is providing some of these community forums. So an example is Pangeo. They have a really great community forum, over 1,000 people on this forum, all asking questions. You can see sharing jobs and stuff like that, asking questions about data, but really providing this open space where it's not oh, you got to go ask your advisor, or, oh, you got to ask this one person, oh, you got to know a person. Really democratizing access to a lot of this information, which has been really neat. And these are really critical communities and forums to be able to engage in open science. And then the other one, so Scott was mentioning this earlier, something we've started over the last year or so is the Open Radar Forum, where, again, we noticed that a lot of the PyArt questions we were getting were more so science questions and not necessarily just specifically about the package. So this is an example of the forum. We've had over 100 people join over the last year. Pretty much every day somebody's on there asking questions and that sort of thing, which has been really neat to see the engagement there. Connecting this all together, so some key conclusions. Start with the idea of what you want to analyze. Find data and tools that enable you to look at this. Develop your workflow, and then share your work with others. I showed Cookbook. You can also do it through blog posts and stuff like that. We've heard lots of ideas about sharing your story, and then also through the community forum. And then some other advice. So find a mentor who can help you along this journey. For me, it was the internship and that sort of thing. Really helped me get started. But definitely find those mentors, and then don't be afraid to share works in progress. You can share your code.
Out for this slide in particular, this is a fantastic encapsulation of what we're trying to do with your take-home project this week. I don't know if you did that on purpose, but it's beautiful. I love it. So just thinking about that, since we'll be heading into that in a little bit.